All right. So this was a discussion where we had one correlation function. What can we learn? But we can also consider multiple correlation functions. So for example, let's consider we have a set of operators that all have the same quantum numbers. Let's say we have n of them, or n of them. All with some quantum numbers q. Then if we take, and I'm just going to, most of what we talk about the t goes to infinity limit. If we look at chi I t chi I dagger of 0, this is going to go like a cubed sum over n. I guess I dropped my p dependency. This is going to behave very much like what we saw before. So the energies don't depend on which operator we chose, right? Because they're determined by the quantum numbers q. The overlap factors, of course, do depend um, on which operator we use, but we don't actually care about the overlap factors. So, yeah. And if you measure this object for all of these different I, then you've got multiple different ways to try and constrain the energies. An even better approach makes use of a Hermitian matrix of correlation functions. So let's call that matrix C with quantum numbers q, and it has matrix elements C, Q, I, J of t, which is going to be chi I of t, chi j dagger of 0. And now I'm going to drop momentum labels and so on. And so this is an m by n matrix. And it will give us sum over n z n I z n j dagger e n t. Okay. Um, so if we think about the vector space that's spanned by the action of these operators on the ground state, then there exists an operator which we will call chi A, which is some sum over I v AI chi I at. Okay, such that chi A on the vacuum is closest to eigenstate A. And so we want to choose the VAI such that we maximize the following. Following quantity. Okay, so you're really trying to choose the linear combination of the operators in our set that gives us the best approximation to a given eigenstate. And so this is really equivalent to try and reducing the contaminating exponentials in, for example, this sum here, right? Um, so we would have that vacuum expectation value of chi A d chi A dagger 0 is going to be some overlap factor. Oops. And so this would then be something that would be dominated by the energy of just one eigenstate. So let's think about what this is. We want to really minimize this with respect to the V's. Let's write this in terms of the V's. So the left-hand side is just given by a sum over I and J. VAI star, VAJ, which I can write in a following way: VAI star CIJ T VAJ, which we can write as a vector VA star matrix C vector A. So we want to minimize this, but subject, because one way to minimize this, of course, is to set the V's equal to 0. So we need some kind of normalization. And so our normalization condition is going to be at some t0 that so this is about some fixed t0. And so we can add that as a Lagrange multiplier. And so what we want to really minimize so looking for extrema, we require ddVA star of this expression to be 0, and that gives us the following. C of t, writing it as a matrix, dot VA equals lambda. And lambda is going to be specific to this given A, so it's got a label A, and it depends on t, and it depends on t naught. C of t naught dot VA. And so this is a generalized eigenvalue problem, which is referred to as a GEBP. Okay, and it's straightforward if you know the C of t0 perfectly to multiply from the left by C inverse and get to a regular eigenvalue problem. But in lattice calculations, we don't know that perfectly, and so there's often ill-conditionedness if we try and do that. Okay, so what do we know about this? The eigenvalues, if you think through this, you can see that the eigenvalues lambda A of t naught are just given by exponentials of minus the energy or an approximation to the energy t minus t naught. And the eigenvectors are orthogonal with a normal in the sense that VA t naught mm, so we can note that we still don't get access to the full Hilbert space. So this quantity A chi A vacuum is going to be less than 1. As the span of is not the full Hilbert space. So I should say these eigenvalues, these are called the principal correlators. And convexity, so the fact that the matrix we started from was Hermitian, um, guarantees the principal correlators approach the ground state from above. And they approach the ground state because in this subspace that's spanned by the set of operators we consider, we're never going to be orthogonal to the ground state. Okay, one last thing that we know about this is there's a theorem called the Cauchy interlacing theorem. And this guarantees that there are at least n true eigen energies below the nth effective energy for any T and T naught. And I think a very important thing to stress is LQCD spectroscopy in this GEVP approach, or in just looking at a single correlation function, is variation, as in the sense that you've come across it in your quantum mechanics classes, and it strictly only provides upper bounds on the eigenenergies. Okay, let me talk about another method for extracting spectroscopy. I'm going to pardon my cat, who's sneezing over there. Okay, so this approach is really based on the fact that the correlation matrix corresponds to a set of matrix elements of powers of the transfer, what's called the transfer matrix. And we call that T hat, which is X of minus A H hat. And so this is the operator that really translates us in time by one lattice site. So it goes from one time slice to next in our lattice simulation. And so Cij of T, which is chi I T chi j dagger of 0, you can really write as some state chi I T hat to the tth power and then chi j. Okay, and it's really useful to think about the linear algebra problem that this entails. So, of course, T is the transfer matrix is an infinite dimensional operator, but we can think about finite dimensional approximations to it. And so the real question we can ask is, given these evaluations of matrix elements between certain vectors of repeated powers of this operator T, what can we learn? Okay. And the Langshos algorithm gives us a way and allows us to extract a subset of the eigenvalues of the full operator T, or an approximation to a subset of the eigenvalues of the full operator T, in doing much less work. So the algorithm, I'll describe it in a few steps, but let me just preview them. So we apply Langshos to the matrix C of T to determine what's called a Krylov space approximation Tm to the infinite dimensional operator T. And that's after m iterations. And as m increases, the approximation gets better and better. Okay, then we're going to diagonalize Tm to get its eigenvalues and eigenvectors. Third, we can, so the Langshos process allows for rigorous bounds to be derived on the eigenvalues that come out. And finally, we'll look at what happens as more and more iterations are applied. Is there some convergence you see? Okay. So I don't want to go through this in line by line, but basically the next page contains the first step of doing this iteration. So it's essentially working through from the correlation matrix, C, right? So we have to make some decomposition of the matrix into the into a product of two matrices, and this is actually entirely arbitrary. You can choose one of them to be one. It's kind of like in the um, GVP, how do you choose T0? Given that, we basically process various steps of this to define objects A1 of T, and then in sorry, let me say that again. So the Langström process is an iterative process that makes use of a recursion relation. So the first step of this is to initialize the recursion relation. So we do that starting from C at time 0, and then make use of C at time t to define A. And then we define a residual. So at the next time, t equals 2, and this is the A1 at t equals 2, minus the A1 squared. And then we can again factorize that into a beta and a gamma. We can iterate to define g of t, b of t, and then finally a2 of t. And then we have what we need in order to perform the recurrence. And the second step here is the recurrence going from the values at iteration j to the values at iteration j plus 1. Okay? And so these steps give you access to uh, the to these quantities A. So having got those, we can then construct this matrix T, Tm. And it is really just a block tridiagonal matrix. Let's see, it has alpha 1, beta 1, beta 2, gamma 2, alpha 2, beta 3, gamma 3, alpha 3. And m minus 1, alpha n minus 1. Okay, and so that defines the mth iteration approximation to the transfer matrix. So we can then, in step 2, we diagonalize Tm as sum over k, lambda k, m, and this lambda k's m are e to the minus ek m. Yeah. And if you can determine these eigenvalues, you have the energies of the system. Okay. Um, so with stochastic calculations of CFT, you're going to get spurious eigenvalues. Some of them be complex and some of them be extremely small. And you need some kind of filtering. Okay. I won't go into the details of that. Um, so the theory of Langlois allows for rigorous statements of how close eigenvalues of Tm are to those of T, the infinite dimensional object. And yeah, I won't go into the details, but you can see a recent paper for exactly how those arise and what they are. But a key feature of this space, because of that, is that Langlois is more than variational. And it provides two-sided bounds. Which is great. And it's also a superset of the GEVP problem. Okay, so I've constructed a data set, and as an exercise, we're going to try and analyze that data set. Okay, so here's another exercise. So taking the HDF5 data file that I've uploaded, which contains Monte Carlo results for a 2x2 matrix of correlation functions for some particular quantum numbers, which do not matter. I want you to use either GEVP or the Langlois method to estimate an energy eigenvalue. And use some kind of resampling method like jackknife or bootstrap to estimate the uncertainty. Okay, so this is going to require some facility with Python or Julia or Mathematica or something, and some careful coding and numerical analysis, and it might take a little while. If you don't have this background, then during the lectures, we'll try and find you a partner who does, and you can talk through it with them. Okay, let's take another little break.